When I wrote my first book in the 1990s, it was actually on software architecture. And the basic tenet of that book was that, and this was how we thought about software architecture during those years, is that we had to be incredibly careful with the initial design of the architecture, as once we committed to the architecture, subsequent changes were very, very difficult to implement and would be very expensive. So we developed techniques to assess architectures, determine the impact of design decisions, predict maintenance costs, and so forth. Then Agile happened in the early 2000s. And of course, what happened with Agile was that software architecture was actually intentionally removed by the proponents of as the notion of an upfront architectural design went against everything that Agile stood for in terms of working software every sprint, responding to change in a fast and agile fashion. And as a consequence, and I think that this was maybe not intended by the people, the proponents of Agile, but we learned that it is actually entirely feasible to undo and replace architectural design decisions in systems that already have a lot of software and the functionality implemented. And of course, out of this grew the architectural technical debt community and the focus on architecture refactoring, which is then a continuous process for every software-intensive system. One of my concerns with the Agile paradigm, my reason for coming up with a strawman proposal like Radical, is that Agile actually ignores architecture altogether. It's simply not part of the paradigm. And we found a way to work around this when it comes to software. But when it comes to systems that include mechanical and electronic components, it simply breaks down. And this is where I believe system architecture needs to be a central element for any product development paradigm that will follow Agile, because in system architecture, we put boundaries between areas of functionality where we can be quick and nimble, and areas where we need to be very careful in predicting future needs, commit to decisions that are once taken very hard to change, and then find ways to work around the limitations that result from these design decisions. And the unfortunate situation is that in most companies that I work with, there is a bit of an antagonistic relationship between people that work with atoms and people that work with bits. But the problem is, or the challenge is, that of course, both parts have to come together in a product. And that's the only way in which we can actually build functionality in anything from telecom networks to systems in defense to vehicles such as cars and trucks. And for some reason, many systems architects have a mechanical or electronics background, and this tends to lead to an assumption that anything that is related to the bits, software, data, and AI, needs to be there in service of the mechanics and electronics. And this is where I think we need to, I disagree simply. I mean, in a digitalizing world where we are increasingly moving towards continuous value delivery, DevOps and all kinds of other approaches, it needs to be the other way around. The atoms need to be architected to support the bits as well as possible. And of course, in the previous video, we talked about the importance of headroom, but it is also taking design decisions where you push as much of the functionality into software, into, for instance, FPGAs instead of ASICs, and find ways in which it makes it as easy as possible to upgrade the system during the lifetime. Yeah, so I think that system architects have to think about at least three things. Platforms is the first one. In my experience, if you have a product portfolio and that entire product portfolio is subject to continuous value delivery, such as we have with DevOps, the best way to accomplish that is very often to create a superset platform where every product basically is a configuration of the platform components. So the superset platform basically includes the superset of all functionality of all products that are present in a portfolio. This has all kinds of benefits. For instance, if you add new functionality to the superset platform, you can then strategically decide which of the products in your portfolio are going to get access to this functionality and which ones do not. It also often helps because you can do a lot of the testing, verification, and certification for the platform as a whole rather than for each product by itself. And if you do this if you do this right, you can spend much less effort on certifying every individual product or testing every individual product, but rather you verify and certify the superset platform. The second question is upgradability. Yeah, many people assume that the atoms will be static and the bits can be cheap to upgrade, can be cheaply upgraded. And that may well be true, but especially in systems that have a very long lifetime, many systems live for 10, 15, maybe even 30 years. The cost of putting absolute bleeding edge electronics into that system such that you have runway for a full 2 or 3 decades is often so high that you cannot build a competitive product at that point. And then it becomes actually much more cost effective to find tools and mechanisms where during the lifetime of the product, you do not only update software, but you also periodically upgrade the electronics in the system. Of course, you need business models for that, but that is typically a point where system architecture and business strategy come together in a close way. So the idea is that, say, every 5 years, you upgrade the electronics or some of the electronics in the product, which then gives you headroom to deliver some more value to customers over time. The third dimension is the ecosystem. So many companies that have successful products or product portfolios in the field are looking for ways in which they can open up the product or some aspects of the product so that customers or third parties can build integration and extensions around the product. And the challenge here is, of course, that it is the architects that define the interfaces that can be used by third parties and by customers. The challenge is the more access you offer, the more stability you have to offer at that point of interface in order to reduce the cost for third parties and customers to maintain their functionality as you are evolving your functionality in the product. So, and again, this is a touch point between business strategy and software and systems architecture, because you then need to decide what to open up, how we can monetize it, and what makes it a justifiable design decision to actually open up on that point. Concluding, one of my main concerns with Agile, and one of the reasons I'm pushing for a next generation of a product development paradigm, is that Agile ignores architecture and basically assumes that we can fix things as we go. And in pure software systems, such as in the SaaS world, this way work just fine, but in systems that include mechanical and electronics components, it simply doesn't work. So we need to have a system architecture that is where the atoms are in service of the bits. We organize ourselves around a superset platform. We support upgrades for not only software and AI models, but also for electronics and, if necessary, mechanics. And we are very careful and strategic in how we open up to the ecosystem of customers and third parties. And with that, I want to end with a quote from Norman Fisher, because I think many of you that are watching this are maybe architects. As an architect, you design for the present with an awareness of the past for a future that is essentially unknown, but your job is to do the best guess possible to take the architectural design decisions that optimally prepare the company for the future.